some more about this uses of this torsion angle in some practical cases. First, if you recall back, one of the main use of this torsion angle was that it can tell you something about the symmetry of it. Symmetry of the involved groups. The torsion angle, I mean, if you have a bond A, B, the groups involved B and C, the symmetry of it will be shown. And therefore, by looking at a set of torsion angles, you can see whether that particular portion is symmetric. If so, what type of symmetry it is. Let us move on to something which is and I will put the name as H1, H2, H3, H4 and C1, C2. Obviously this falls under this category. And we said there are 4 torsion angles here, and let me write it as H1, C1, C2, H3 as chi. Call that one as chi, value is chi. Then H1, C1, C2, H4, we know will be chi plus 180 because it is sp2. Now we are going to ask the question H2, C1, C2, H3 and H2, C1, C2, H4. How will that be? Now if you look at it, there is a C1, C2 bond we have taken. So H1, C1, C2, H3 is chi. Therefore, H3, C2, C1, H1 is also chi. C1 is sp2. If H3, C2, C1, H1 is chi, H3, C2, C1, H2 will be chi plus 180. H3, C2, C1, H2 will be chi plus 180. And similarly, we have seen H1, C1, C2, H4 is chi plus 180. Therefore, H4, C2, C1, H2 is chi plus 180 plus 180, which is chi plus 360, which is chi. And therefore, this will be chi. So, if you know one of the torsion angles, you can know not only the 4, but if you know the positions of it, you can also see some of them are, 2 of them are chi, 2 of them are chi plus 180 degrees. But this relationship does not tell you immediately whether this molecule is planar or not. Now, if assume that this molecule is completely planar, then by just looking at it, you can see H1, C1, C2, H3 will be the plane and H1, H3 on the same side of C1, C2. Therefore, this chi will become 0 degrees. So, I will write here what will this be if there is planar. This will be 0 degrees. Once this is 0 degrees, the rest of them can easily be formulated. This will be 180 degrees. This is again 180 degrees. This will be 0 degrees. So if it is exactly planar. But practical cases, you won't find some other things you find they are not exactly planar, ideally planar, perfectly planar, any other things you can use. In that case, I'll just put it as, we call it planar if it is roughly of this. How much roughly is, I cannot exactly say, there is no hard and fast rule, but you have to use some, what you may call, common sense and also experience and all the things will tell you. If it is 3 degrees, do you call it planar? If it is 0.1 degrees, do you call it planar? 3 degrees is not planar. They are also not very clearly defined. But one thing is clear, if this is 20 degrees, instead of 0, then this will be 20 plus 180 will be 200, which is equal to 200 minus 360 is minus 160. And so the combinations will be 20 minus 160 minus 160, 20. And therefore that will not be, that can say that is not planar. Therefore, which is not planar can easily be said. Just it gives you a feeling for that, that's all. Just like you say somebody is tall, somebody is short, though they are relative. But in general there is a consensus agreement that you can't call a very tall person a short and short person a tall normally. So here also this is the idea about it. So one of the things you can see is when there is an environment like this, the set of torsion angles immediately tell you whether they are planar or nearly planar or not planar. Now the another example I am going to take is this is where I stop. Two possibilities. I can put double bond here, double bond here, double bond here, or I can put a double bond here, or a double bond here, and double bond here. Or if I want to be more orthodox, I can put it as to indicate sort of a pi-electron resonance system where this is resonance structure. Neither one of them is a double bond, neither one of them is a single bond. It's partly a double bond, half the double bond, half the single bond, 50% of it, of this and that weightage, etc. You can say. But we are not concerned about that chemistry orthodox level. But we will now see that when such a situation occurs, you end up with a molecule which is of this type. Obviously, the whole thing is planar. But we will just not simply say whole thing, all the thing, all the atoms are in one plane. That's one way of looking at it. But always we will now try to put it into that some sort of a idea about the torsion angles. Now, if you have look at it and look at this, you can easily see that this, if I take this portion, let us say C1, C2, and take that as the C1, C2 here, then you have a H, 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 H. Here you have a H and C, H and C. Rest of them are same appearances there. Now, if you look at the torsion angles which we are looking at it here, we can see that there is a C1, C2, C3, C4, C2, C3, C4, C5, C4, C5, C6, C1. This type of torsion angles all involve atoms which are in the ring. And so, sometimes they are called internal torsion angles. And it doesn't need much of effort for us to say that if you take a planar molecule of this type and then you can put everything in one plane, all these internal torsion angles, all of them will be 0. If it is a perfect planar structure. Again the same thing, if it is an exact planar, then it will be 0, 0, 0, 0, 0. If it is roughly planar or nearly planar or almost planar, then they will be deviating from 0 degrees slightly on either side. So when I say deviating on either side from 0 degrees, remember that 0.5 is a deviation from 0 degrees on one side, whereas minus 0.5 degrees is a deviation on the other side. Modulus of it will still be close to 0. Again, here there is only a rough idea as to which you call planar, which you call distorted planar, or totally non-planar. Same idea as we said here applies here. Okay, now you can also see that since this involves all of them are carbon here in the benzene ring, all the internal ring angles being 0. If you consider any combination of 4 atoms forming a ABCD system in which obviously none of the CHs can become a member of the middle bond for a torsion angle because the H does not have anything apart from that. So any CC bond if you take and you have a H here and a H here and try to find out H1, C1, C6, H6, that will also be 0. On the other hand, if you take a H1, C1, C2, C3, that will be 180 degrees. Or in other words, if you know the structure of this and if you find out that a set of torsion angles are all coming to 0, and also the ring is closed from the bond length, bond angle considerations, then you can say it is a planar 6-member ring. But the main point to note is when there is a planar ring, whether whatever if it is substitution here going like this, will always be around 0 or 180 degrees. Therefore, 0 and 180 degrees are something which is closely associated with planarity, and planarity is something which everybody likes. You are happy if you get something which is planar because it saves you a lot of botheration. Very nice, obedient confirmation. Now, similarly, if I take this idea is now, as I said, this is a linear molecule, which is again planar. This linear system, which is planar, linear molecule also you can say, because this is a 3D. This is again a cyclic system, which is planar. In this cyclic system, you have a 6-member ring in the cycle. You can also have other similar things like please put up with me if I make some mistakes in the valency part of it. This type of rings also can come across. Again, it is a 5-member ring. Again, the concept is you have 5 atoms forming a ring. So you can have 5 internal torsion angles, and all the 5 internal torsion angles will be nearly 0 if it is planar. And again, external torsion angles, as I said, if it involves the one which is in the projecting here like this, then it will be 0. If it is a combination of something which is external and then the others are being internal, then it will be 180 degrees. So many of the characterizations, if you have the set of torsion angles, becomes almost unambiguous. Okay, let us take something which is more, little bit more complicated. This is also a 6-member. So I will remove this part of it. Now I will take the counterpart which is close to this benzene. Same 6-member ring. I have put all the 6 carbon atoms in the ring. But the only thing is each one of them is in sp3 level. And I am now going to just keep these things without any atom. Of course, there is an atom there, let us put that way. Or if you are so keen, you can put H everywhere here and call it a cyclohexane. Now, we ask a few elementary questions with this system first. In the earlier case, we took the 6-member ring, which is planar, and put it on the board, and we simply derived, said these are all the various angles 0 and 180 and so on. Here it is not that simple. But first, let me go in a slightly complicated way and come back, make it as a simple later on. Now, suppose I start from one of the atoms, let me call this as C1, and C2, C3, C4. This is a ABCD system, and this has a torsion angle. Having come to C4, let me take C2, C3, C4, C5, that will have another torsion angle. And then C3, C4, C5, C6, that will have another torsion angle. Suppose I build the molecule and go on generating it. If I give the torsion angles as I please, then there is absolutely no guarantee for me that this atom will come at a bonding distance to the first one and with the correct bond angle at these places. Or in other words, the moment when you have a closed system like this, the torsion angles, which of 6 of them are here, cannot be considered as all of them being independent. The loss of independence is necessitated because the system that you are having is a closed ring system. But since this is one of the important systems which occurs in the realm of sugars, polysaccharides and so on, it's nice to know a little bit more about it. Again, I go back to the well-known thing which everybody knows. This is a 6-membered ring. I have taken a model in which I am not going to bother about the torsion angle, but I am going to close it in a way such that the thing closes. And if my lengths of these rods are all exactly taken, or correctly taken, then I know that if it closes, it will close at the proper bond length. And if I have taken the jack as the tetrahedral, I am sure when it closes, unless I put a lot of pressure into that, it will close at the proper bond angle. So the model is always the best thing to learn. So I start with the same model again. Now, in order here, you can notice I have just specifically put the 6 bonds in 6 different colors: white, green, black, red, yellow, blue. Now, I have just want to prepare a table in which, in this arrangement which I have in my hand, in this model, what are the rough internal torsion angles? Okay, so I will say the bond which I am going to look at it, about which the torsion angle I am going to talk of, which is the bond BC, is the internal or the ring bond. And the atoms involved are also the ring atoms. Therefore, the angles, the torsion angles I am going to get here are all internal torsion angles. Now, I am going to quickly go through that. And you believe me what I am going to say when I am writing on the board. So first, I am going to take, let us say, about the bond which is blue here. And I am going in this direction. So, I will first have to have a blue, then white, then green, then black, then red, then yellow. That means these form the bond BC. Since I have considered only the internal torsion angles, the other 2 atoms A and D are automatically fixed for me. So now let me just look at it only one and keep it this way. For you, keep it here along the blue and keep this one up. This one you will notice it goes in this direction, which means for you, if it is there, it is an anti-clockwise rotation, and so the angle is minus, and so I am just going to say the torsion angle chi for that is, let us say, minus 60 degrees. The next bond is white, so I am going to take the white and keep the yellow up here. Sorry. White and keep the blue up here, then this is on this side. And you can assume, take it from me, that this is plus 60 degrees. So, if I do the whole exercise carefully, I will be since the molecule is a cyclic molecule, the next one is to go, it will come back here and so on. So, you have a set of torsion angles which in an ideal structure like this has alternatingly plus and minus about 60 degrees. That is what is well known as what is called the pyramidal system. So if you have a set of 6 atoms and you find it forms a ring, and your doubt is just to see whether it forms a planar ring like benzene or a pyranose ring like this, you need to calculate only 6 torsion angles, and with the help of the present graphics and the other computer available, it is much easier, very much easier. Child's play, even I would say kids, I would say earlier kids play, now it is really child's play, and a child of 1 month old is the one which I will say for the play. So with that, if you do the job, you simply have to click or do something and get the 6 values, look at it collectively. Then immediately answer to you, glance to your eye, okay, this is a planar molecule. Oh, this is a pyranose type of thing. Now, not only the pyranose, I am making a small, I am not very, people who know the whole thing will say that I am not very specific and I am not very specific, they will come to the grade. But this form is called, the so-called, as I said, the chair form of binomials. That's what I said, I am not very specific. Though it is 6-membered ring going like this, the binomial, what we are now looking for, seeing here, is what is called the chair form. And towards the end of the last lecture, I said, this is calling a chair form. It's a little bit, I would say, though it is yes and no answer. It is a chair, you sit here, put your back here, put your leg here. But you comfortably sit here, I will say, is a chair form. But whatever it is, now having this set of torsion angle gives you, it is a chair form. Now let me ask you, we are going to see a little bit more about this chair form of binomials because this occurs almost everywhere if you are going to deal with conformations of sugars, polysaccharides and such things, which are also biomolecules. Now, so first we will ask the question, how to qualitatively describe this one first. Usually we do it qualitatively, go back to quantitative things. This time I have reversed the role. I have made the quantitative things first. Now let us look at it. First thing I am going to look at it is that I am going to take this molecule and keep it on this cardboard. As just for the time being, assume that though this is a small fellow projecting here, assume that it is not there, and so this atom and this atom is sitting on the plane of the board. Where do you find the other three atoms? This and this are all above on one side. Not only that, any three atoms will form a plane obviously, and this is the plane, and if you keep another one which forms the plane, this and this will become parallel. So one way of looking at it is the plane formed by the alternate atoms of the ring, either C1, C3, C5 you take, then C2, C4, C6, the plane formed by that will be above this and parallel. This you can see by putting any three of the thing, and obviously this is one way of looking at it. The second way is a little bit more involved, and that is the one which gives it a form chair. Now let us look at this in this way. Suppose I call this as C1, C1, C2, this is C3, C4, C5, let us put it. C1, C2, C4, C5 also, if I put it here, you will find that this forms one plane. That is, these four atoms form one plane. And where is the C3 and C6? One is below the plane, another is above the plane. So another qualitative way of saying about it is, take set of four atoms in which if you take C1, C2, leave C3, C4, C5. Or if you take C2, or if you take this C3, you take C3, C4, leave C5, C6, C1 you take. Or take 2, leave 1, take 2, leave 1. Then you will find this is the plane, one up and one below. So qualitatively you can say that the chair form is something in which a plane is formed by these four atoms, of which none of the three are consecutive. The others, one will be up and one will be down. So you have different ways of looking at the molecule. So long as you have a model, you can look at it and immediately say. So long as it is in a graphics, if you know how to properly rotate the molecule, you can do that and then say. If you look at it in this way in a model, in a graphics, you will not be able to differentiate whether it is a planar or a non-planar. But if you rotate it like this, then you will see that. But when you rotate, so many other things also will rotate, so it may go behind something, you may not see it also. The best way is if you know the torsion angle set, look at it, then you will be 100% sure what your answer will be. Now, in this connection, let me go to another small aspect. Okay, now let me take this as the this is again the same thing, except that I have removed the color from the bonds. I have put all of them are black because now what I am going to say doesn't doesn't matter which bond I am going to talk about. But now let us look at it again qualitatively and from the point of view of space and now if you look at it, at each place you have two bonds going out of it. You call it two bonds going. And then if you take here, there are two places where I can put my bond. Here there are two places where I can put my bond. Here I can put my bond like this. Now, if I keep it in such a way that the three are in one plane and the other three are in another plane, you will notice immediately here that if I am going to put a bond to represent the bond that goes there, I have two options. Let us take this portion. I can put the bond here or I can put the bond here. Okay, now I put the bond, let us say here. Now you see, when I put the bond here and without disturbing anything, this bond is almost perpendicular to the plane. So this direction, you call it axial direction. On the other hand, if you don't want to put the bond here, and if you want to put the bond here, you will find that this bond is not exactly parallel to the plane, but slightly inclined to the plane, but it is not perpendicular to the plane definitely. So you find that this is what is called an equatorial direction. This is again qualitative. Now, so I will now put an equatorial bond at one place and put another. Okay, let me go to the next place and then look at the situation first. Okay, if I had put an axial bond, I will put the axial bond in white with a small representing normally the hydrogens, and this being an OH sometimes in the glucose business. So I am putting this small one as axial. This is equatorial. Now when I come here, I find that this axial is pointing not in the up, but it is pointing down. This is not perpendicular to the plane, but this is perpendicular to the plane, but it is going in the opposite direction. Therefore, this becomes the equatorial. So it is not the perpendicular bond going up or down, but it is perpendicular, that's all. That becomes axial. So once the axial is fixed, the other one becomes the equatorial. Now, let me now look at around this bond, about which I have put one is the ring atom, ring bond, one is an axial bond, one is an equatorial bond. Here again, one is the ring bond, one is an equatorial bond, one is an axial bond. So here white is the axial, black is the equatorial. The ring is clear, we don't need to specifically mention it. Now let us look at from here what will be the torsion angle with respect to this ring. Now you will find that if this one is a ring atom, ring atom, ring atom and a ring atom. Therefore, this has to be plus or minus 60 degrees. And if you look at it to say it goes on this direction, therefore it is minus 60. Then you look at the other equatorial thing with respect to the ring atom. This is 180 degrees. Because we know it is a three-fold symmetry, and therefore if any one of them is 60, you have a 60, 180, minus 60 will be there. So one of them is of the 60 or minus 60 is taken by the ring atom, leaving for us 180 and either plus 60 or minus 60 depending upon which is the ring torsion angle, of which the 180 you will find goes to the equatorial position. Let us examine the same thing with respect to this equatorial also. Then this equatorial, let us say, suppose it forms about this bond, I am looking at it. Then I keep it here, I look at it this way, this, 180 degrees. Or this being part of this bond also, if I look at it from this direction and look at it from here, this is 180 degrees. So I am not giving this, I am just showing to you, or one example I am giving to you, that if you want to study a molecule with a Pyranose chair form, then these torsion angles, if you know about them clearly, if you can write it down as a ready reckoner, then whenever you have a system to find out whether it is equatorial or axial and so on, in a practical case, the torsion angles will come in a very handy way. Not only in a very handy way, there are almost foolproof method of saying which is axial and equatorial. I am not going to now put the idea of how to represent the equatorial and axial, and those of you from the physics and other stream who don't know about it, please check up with your friends, with people who know about it from the books, and see how conventionally these axial equatorial are represented. Chemists definitely they know the stereoisomerism, and so they know well. But the others, I would like you to supplement, because that is not concerning the numbers, but that is concerning the way of representation, which is also important in the long run. Because many people will just represent it that way and ask you to, make you understand what they mean, for which we should know how it is being represented. So, with a simple set of torsion angles, now we are now able to get a lot of information about the nature of the ring, about the, not nature, about the geometry of the ring, about the shape of the ring, you can put it that way, that's a much better usage, about the substituents when they are, in what way they are with respect to this, because everybody will understand if you say they are all axial, they are all equatorial. In glucose, if you take all the side groups are all axial, or if you take some other thing is equatorial and so on. And those of you, again from the physics, I would like you to do some little bit of reading of what are called the nomenclatures with respect to this. And this, I found it at least interesting. I'm a physics student. When I read it, I found it very much interesting, because there is something which they call it all alcloses gladly make gum in gallon tanks. Does it make any sense to any of you? All alcloses gladly make gum in gallon tanks is something to remember, that we have an allose, alclose, galactose, mannose, glucose, either glucose, etc. I don't exactly remember that. But that will tell you how to go from one to the other. Because at each place, if you take, there are 4 places in which you can put axial this one, equatorial this, axial this, and get thoroughly confused and baffled. So this is one of the ways by which to know about it. It's very interesting to read it as a sort of a thing to know how the things are axial, equatorial. And if you, some next stage, if you are terribly interested, you can take a molecule and try to work out some of the things and see how they are. But make sure that every stage you come back to the torsion. That is very important, at least for us. Now, the other member, which is again comes important, takes importance in the biomolecules, particularly in nucleic acid, and also in some side group of amino acid, or the 5 member. As I said, the planar form of the 5 member ring, let us say, looks like this. Go to history, or you go to tryptophan, you may come across this somewhere around. So, the 5 member ring, planar, again planar is planar, no problem. 4, 5, 6 or 7 or 8. All the internal angles are near 0, very easy. But the other one is not as elegant as the 6 member ring. The other 5 member ring, where you again have this type of thing, except that you don't have this fellow here. Pardon me for the unscientific way of doing it. You have a 5 member ring, let us say put CH for example. Now this definitely is sp3 each places. And now if some of you are interested a little bit more of geometry, you can say that if you have a regular hexagon, there are 6 sides, regular hexagon, and some fellow has said in mathematics that if it is a regular figure like this, you add all the external angles, it will give 360 degrees. So all the external angles are 360 degrees, means everything is 60. Therefore internal angle is 120, and 120 is sp2. Therefore benzene is sp2, benzene is planar, benzene is hexagon, and so on and so forth. If you come to the same thing with 5, if you do the same exercise, you will find 108 degrees to be the one which forms this ring if it's all of them are the same. But 108 is near 109, 110. So it is a tetrahedral thing. So something is happening here, but I am leaving it to you to look into that to see what it is. But the main thing is, if you do the tetrahedral part of it, then each one, let us say, is about 110 degrees roughly we take it. Then external angle becomes 70. 5 into 70 is 350, and therefore with 110 degrees, with all the things being equal, you cannot get a planar thing. Whereas with 120, external angle being 60, 6 into 60, 360, therefore you could get a planar thing. So here, what is the one that we are going to see that? Again, here the ideas are all is a little bit not as clear as our Pyranos. Excuse me, before I leave this fellow, one more thing I forgot. Two things I forgot. Now, I'm going to just going to do a trick. Because it's a plastic model, I could do whatever I want, and I have not broken any bond. So, but how much of energy it has to be given to do that, don't ask me that question now. You'll reserve it for a 300 level. But now, this is also a 6-member ring. It is closed. But now you see here, this is a different form in which this is called a boat form. So, what will be the type of, this is, I will call it as a chair form. What will be the relationship of the angles for the boat form? I forgot to, I should have come to the 5-member ring after that. Now, first of all, I am put the other way around, I am going this time. Last time, I did the torsion angle and came back and then explained to in terms of plane. But now I am going to explain in terms of a different way. And if you remember our 6-member ring, there was the colorful 6-member ring. This is the one, sorry. Okay, I will take this one, this is also fine, this is the background. So, I said you take alternate things, put it on plane, the other three are in another plane parallel. And if you look at it this way, you have 1, 2, 3, 4 which forms a plane. One is up and one is down. The difference is both of them are up or both of them are down, depending upon whether you are going to look at it from below or from above. So, if you take this particular arrangement, again the alternate things form a plane. C1, C2, C4, C5. C3 and C6 are on the same side of the plane formed by the C1, C2, C4, C5. And therefore, this arrangement is called the boat. So, it has a set of torsion angles defining the boat. Just as I did earlier, I can go into that and then see what is the set of torsion angles these things are. And there is something more in between. If I really do the trick in front of you without thinking that I am not a magician. So earlier I had it this way. I know I slowly brought it like this and went it this way from chair to boat. Now suppose I give it as an intermediate stage, which somehow with the distortion and all those things, etc., I will find that this is a thing where there is a platform and there is a thing to stand on. I will call it a beach, whatever it is, sit there and so on. But you find that this one arrangement, there is a different arrangement in which 1, 2, 3, 4, 5 in a plane and 1 outside the plane. This is called a half. Door, when it is open, fine. When it is shut, fine. If it is not, what do you call it? Half open, half shut. Half open equal to half shut, therefore open equal to shut. Famous thing in mathematics to show that how upside down can go by using the thing. But there are some other people have come up with something to show why it is not so. That's a different thing. So here it is a half chair. It's not called a half boat, but it's called a half chair. So there is one more thing called a half chair. And what will be the type of torsion angles which involved in this half chair? So we have a chair, you have a boat. I just add here half chair. Now in this will be a set of torsion angles which defines that form. In other words, when you have a set of torsion angles, immediately you can know how the ring is, the geometry of the ring is or shape of the ring is. Similarly, when you come to the 5-membered ring, how do we go around doing the job? First, planar we have said. Second one is the one in which you have 4 consecutive atoms in one plane. And so what will be this torsion angle? If you look at it, it is 0. Because it's up like this. So you have 4 in one plane and 1 out of the plane. In that case, you will find that this torsion angle is 0, others are different from 0. How much is different? What is the sign of it? Roughly what it is? I want you to take the model. If any of you want, I can give you that also from my lab. Or you can yourself generate it using some 5 tetrahedral jacks and 5 small rods. If you have it, I think you can do it. That will be also very good. And see, look at it and see what is the type, how much the torsion angle is. More than the actual value, the signs are very important. So you start from here 1, 2, 3, 4, 0. 1, 2, 3, 4, how much it will be? 1, 2, 3, 4, how much it will be? How many you will get? 5 you will get. There is another one in which 3 of them you keep it in one plane, 1 above and 1 below. So one of them is called envelope, one of them is called the half chair, and so on. But the main thing is with 4 in one plane, 1 out of the plane is usually encountered frequently, and sometimes it is called, this atom in the ring is puckered. So one of the words which is commonly used is what is called the puckering of the ring. So you can say C gamma puckered or C beta puckered, or in the ribose or the ribonucleic acid, some other thing will be puckered. Endo puckering, exo, we will come to the endo exo later on. But the puckering is something which is associated with that. In other words, it is not a plane, something else is gone out of the plane, that's called the puckering. If you are still more want to do it clearly, go to the dictionary and find out what it says. Puckering means what. Okay, but for us it is enough if you know that whenever you have this 4 roughly in a plane and the one which is out of the plane, that is normally known as the puckering. And this is prevalent in the 5-membered. So we have said, so these are some of the uses which we can put the torsion angles to, and I have only taken one set of things, namely cyclic ring systems. You can use it in any system you want. You can use the torsion angle to your best of benefit depending upon how much you are going to involve yourself in a particular system. Because each one will have its own set, you can define it. It's very good, very useful in comparing 2 structures if you want to know whether they are having the same thing. Because 2 structures, when you take them, they will be with respect to different coordinate system, and you would like to know whether they are the same conformation. Then this torsion angle is the one that's more important. Okay, then we have to move to the next stage. The next stage is something which is totally different. So far we have seen that calculation of this torsion angle is from the orthogonal coordinate system, for which that means x, y, z are given to you. But there is another branch of conformation which is now used widely, and the general, very popular, very catchy name that you have got for that pertaining to conformation, pertaining to molecules. This is a general term used for so many other things, but here we are confining it only to molecules and anything to do with molecules. For that, many a times you would be interested in building up chains with a given specific conformational parameters. What are the conformational parameters? Bond lengths. What do they depend on? Atoms and the type of bond. Not very much varied. Bond angle depends upon the state of hybridization and again it is not going to vary very much. Whereas the third member, torsion angle, is going to change a lot. Therefore, when you are many times when you are talking of the modeling, actually what you are doing is given a set of torsion angles, or given a set of torsion angles, and assuming the bond length and bond angles are all reasonably stationary, you try to generate the molecule and then look at it for various other things. So one of the things that we are going to see in the next after a few lectures is what is called the Ramachandran map. For that, it is almost like, without saying it is a modeling, the whole thing started with modeling. Therefore, the first thing we are going to now see in a bit more mathematical way, or a bit of mathematical way, I won't say more, but more conservative way, I have not talked about anything. So, you take, say, some system, first ABC. We have so far addressed the question, if there is an ABCD system, how to find the torsion angle. Now I am going to put the cart before the horse, and turn it around and make the cart as horse, horse as cart. So I am going to ask the question, I am interested in getting an atom D . In other words, I am interested in getting the position of the atom D. Or in other words, I am interested in getting the x, y, z coordinates of atom D when the x, y, z coordinates of A, B, C are given to us, and we are also given what is this bond angle, and we are also given what is this bond length, and we are also given what is this torsion angle. This brings me to a small side, I will call subroutine in my language, that you have now able to write the angle, which is very simple. Everybody writes it as tau. You can put an angle like that and write it. You can write the length like this, no problem. But how to represent in a thing a torsion angle, I have not told you yet. So this is an occasion for me to say. Now, please follow this a little carefully. Ready? Now, what was our definition of the torsion angle? You are looking along the axis and rotating it the farther end in the clockwise sense. Now, if you are looking along the axis like this and you are rotating it in the clockwise sense, then you will see that my arrow, I have to put it like this. So, what are the things you should not do according to this, what I would say, should not do, is don't write like this and put your thing like this. No. Or don't put like this and put the arrow here. No. This is telling you a lot of things. You are looking along this direction and you are rotating the farther end and you are rotating it to the clockwise sense. All the conventions are embedded in this. Either you can put it this way, or if you don't want to put it that way, you can leave it like this with a little break and then put it that way. That is artistic. But what is important is your curvature is such that from B to C, if you put it that way, B should be within that curvature inside. And the arrow should be downhill here. So wherever you are talking of the thing, suppose if I have a molecule of this type and I am wanting to do the thing here, you have to put it this way. That is the convention. But 90 out of 100 people are not following this convention. But you better do it systematically so that you will know that if some of you write this and give it to you, you understand it among yourself at least correctly. Okay, so the way in which to represent the torsion angle is just putting an angle sign, put an arrow and write on the top of it what the symbol is. But the problem now we have is how to fix the fourth atom. This is called we call a fourth atom fixing. So 1, 2, 3, fourth atom fixing. Now, earlier we said bond length simple, only length, root a square root, nothing else. Bond angle, a little bit more complicated. You have to take three things and find out this by division and so on, or you take the direction, cosines, etc. And when it came to the torsion angle, we said we went to a vector. I said the way in which we can do is take the thing, get the cross product, do a lot more things and come out. When you come to this stage, you enter the fourth member, namely, something called matrix. So those of you again, it's a little bit weak in matrix. I don't want you to read the matrix theory, but to know what matrix is. Now this type of matrix, we will come back, we will do that, is called, I will call it rotation matrix. And according to the matrix convention, this has got 1, 2, 3 rows, 1, 2, 3 columns. Therefore, it is a 3 by 3 matrix. And now, I have specifically indicated by the M and put one subscript under one superscript and one subscript. If you remember our definition, a rotation about a bond is a direction, and the direction has got a direction cosines, and this L and M gives you the set of direction cosines. And you are rotating about an angle, through an angle, and that angle we call chi, and that is chi. And what is the sense of rotation? Clockwise. What is the, again, further viewing along the axis? The farther end is rotated clockwise. Under that assumption, then the full matrix in this one is like this, where this, and this are ones, this and all the other things are L. Sometimes. Okay, don't need to write it down immediately. I can give you a copy of it for you, those of you who are interested to note down fully. But please note that this matrix is a little bit more, have a lot of trigonometric things coming in that and so on. So, but essentially, this gives you a tool by which you can form the matrix. Now, those of you who are interested in doing that, I would suggest those of you who are a little afraid of it, please do it for any one set of element with the chi and just form the matrix. You will find it minus 0.2311 like that, very simple to look at it afterwards. Do the actual thing. Now, for what are the elements to take? You can take any element such that L square plus M square plus N square is 1. But don't go on searching for that. You can take any, let us say, something you want. I will just take something. It's not that all of you should take this. You can take anything like, let's say, 0.25 minus 0.25 as L, minus 0.62 as M, and find out M such that L square plus N square is 1, and take whatever the plus or minus sign you need, you get a set of elements which are normalized. Then have some 50 degrees as your chi. Then form the matrix. That is first stage. Second, branch off two things. First, who want to do it by symbols. Others who want to do it by numbers. I want you to do that when you have an LM, particularly LMN, and a chi, you form the matrix M. And do the same thing with minus L, minus M, and chi, and get a matrix. And L, M, N, and minus chi, minus L, minus M, minus M, minus chi. You will find the numbers involved are the same, but the positions may be different. Just fun of it, for the fun of it. There is nothing very great science involved in that. But just for the fun of it, if you do that, then first of all you get the, just like writing a thing again and again as a copywriting to improve your handwriting. This is something like arithmetic copywriting. So you can do that and then see how this thing looks like. This is the matrix that's going to be, we will be using it. So from now on, next class, I will be saying the matrix M with respect to this. I will not be giving the data, full detail.